Okay. Well, shoot. Hang on a minute. I don't know. All right, like I said. Well, it still doesn't work, does it? Way back in chapter 1, we saw this slide where we talked about matter, simply defining it as anything that has space and mass, elements, simplest form of matter, and we said we could take two or more elements, put them together, and make a compound. Compounds can be two types. We'll learn about those today. This is methane, natural gas. One carbon in the middle, four hydrogens. They're always present in exactly the same shape and pattern. This is what's called an ionic compound. Ionic compounds differ from molecular compounds because in molecular compounds we share electrons between adjacent atoms and we form what are called covalent bonds between them. In an ionic compound, we have ions that are positive and negative, and they simply attract each other and form a unit crystal. This represents sodium chloride, the unit crystal for NaCl. Covalent bonds come in three types. Single bonds is what we saw. These are single bonds. They also can form double covalent bonds or triple. Each covalent bond can only contain 2 electrons. This double bond would contain a total of 4. This shows the ions in sodium chloride. Again, the sodium cation, that's positive, simply attracts the chloride anion. Depending upon their shape, they aggregate, their size, they aggregate into a given shape, and that's the unit crystal. Sodium cation, chloride anion. We'll talk a little bit more about the nomenclature in just a minute. Now, when we were doing electron configuration, I said the thing that we were interested in from electron configuration was the valence electrons. This represents carbon. Carbon is in the second period, so it's right here. That means the first period is full, 2 electrons, 1s2. And in the second period, we have the 2s electrons, and we have 2 p electrons. The core electrons are the 1s, they're here in the middle. They don't do much, they just sit there and neutralize the charge. These are the valence electrons. They're the highest energy electrons in any atom. And these are the guys we care about because these are the ones that are going to make covalent bonds. Covalent bonds. There's a simple mechanism to display bonding in covalent or molecular compounds. And that is the Lewis dot structure. G.N. Lewis was a chemist and came up with this very simple method. Now it's important to remember that when you write a Lewis structure, it's just bookkeeping. You're just doing bookkeeping on valence electrons. But there are rules. Let's start with carbon. Carbon is in the second period, once again, right here. These are the core electrons, and we have 1, 2, 3, 4 valence electrons. Lewis said, what you did is you write the chemical symbol, and then you place the valence electrons around them, one at a time, unpaired, until you get 4. This is all the electrons we have for carbon, so this is simply the Lewis structure for carbon. Very simple. Now, if you have more than 4 valence electrons, Lewis said you put 4 in first, and then you start to pair them. Let's look at fluorine. Fluorine is in the second period here, and it's in group 7. Once again, that means that the first period is full, S1, S2, and it has 1, 2, 3, 4, 5, 6, 7 valence electrons. So to write the Lewis structure, we would put F for fluorine. We have a total of 7 valence electrons. So the first thing we do is put them in one at a time. Then we start to pair them. Now, remember, I just said Lewis structures are simply bookkeeping. So that means it doesn't matter if you draw it like this, like that, like this, or like that. They're all the same. All you need to make sure is that you have 3 pairs of electrons and 1 unshared pair. Any questions? All right. Valence electrons. We can look at the periodic table and we can count and figure out how many valence electrons we know. Okay? But there's a simpler way. Remember when we were talking about groups in our periodic table? We said we would number these 1, 2, 3, 4, 5, 6, 7, 8, and just ignore all these guys in the middle. Well, the reason that we just do the representative elements here in our groups is that this corresponds directly to the number of valence electrons. Group 1, 1, 2, 3, 4, 5, 6, and 7. In group 8, we have the inert gases. They have a complete set of 8 valence electrons. Remember, the inert gases are very, very unreactive. Let's start off by looking at simple atoms, and we're going to make charged atoms out of them. The nomenclature, if we have a positively charged atom, is called a cation. If we have a negatively charged atom, it's an anion. Now, to make the Lewis structure for an anion or a cation, what you do is simply start off with the basic Lewis structure for the atom. Let's look at chloride anion. Chlorine is here in the third period. Third period, it is in group number 7. So we have 7 valence electrons. The chloride anion has a -1 charge, and we show it with the superscript minus. If it was positive, we would do a superscript plus. So we'll start off with chlorine. Once again, we're in group 7, so we have 7 valence electrons. We will place them around our chlorine, one at a time, then we pair them up. Now, this is neutral chlorine. Okay, it's neutral. To make the chloride anion, we have to add 1 extra electron. And we do it here, where the unpaired electron is. And we show we have a negative charge. Any questions? Let's do another one. Sulfide dianion. Sulfur forms an anion, negative, with a charge of -2. We find sulfur in our periodic table. It's here in group 6. Okay, that means we're going to have 6 valence electrons, right? We'll put them in one at a time, and then we'll pair up. So we have 2 unshared electrons. We have a -2 charge on our sulfur. So we're simply going to bring in 2 electrons and pair them up. And show a 2- charge. Nitrogen. Nitrogen is here in group 5. It will have 5 valence electrons. It forms a -3 anion. We put our nitrogen, we put our 5 electrons around it. We're going to add 3 more to give this a net -3 charge. Let's look at a cation. How about sodium? Sodium is here in group 1, so it has 1 valence electron, doesn't it? So we have our sodium, we'll add our valence electron. Now this is neutral sodium. To make this positive, we need to have more protons than we do electrons. So we're going to take this electron and get rid of it. When we do that, it leaves the sodium with a net positive charge. Now let's think about what we're doing here and why. What we're trying to do as we add or subtract electrons is to take the atom itself and give it what's called an octet of electrons. This is the octet rule. Remember we said that inert gases here in group 8 have 8 valence electrons. Their shell is totally full. The unpaired electrons are what we use to make bonds. That's why these are very, very unreactive. They don't have unpaired electrons. So, the octet rule simply says you want to add or subtract electrons to your neutral atom in order to form an octet. Makes it very stable. Let's see what we did. We started with chlorine. Chlorine is here in group 7. We made chloride. When we did that, we took chlorine, which is in group 7, and we gave it the same configuration as argon, the inert gas. We took sulfur, here in group 6. We added 2 electrons and made a dianion. Once again, this gives us the configuration of argon. Sodium. We had 1 electron here. We got rid of it. And we formed the sodium cation. Sodium starts here. When we get rid of this electron, we wind up with the electron configuration of neon. The whole point of this is to generate 8 electrons in the valence shell. Make sure nothing is unpaired. Now the only exception here, of course, is group 1, because group 1 can only hold 2 electrons. If we had hydrogen as one electron, if we add an electron to it, we would get helium. But it can only take one, so this is like a duet rule. Okay. Any questions?
Yeah. Would it be possible to take the electron, the only electron hydrogen has, just like we did in sodium?
Hydrogen?
Yes.
It'll start off the same as sodium with one electron.
Yes.
And then you would get rid of it, and you would make the equivalent of helium. All right. We've made ions, and we've showed them using Lewis structures. We started off talking about covalent bonding. I said that in a covalent bond, you have two electrons that are shared. Every covalent bond only can hold two electrons. Chlorine in nature appears as Cl2, two chlorines stuck together with a covalent bond. To do that, we're going to take a neutral chlorine like this. We're going to bring in the second one to make CO2. These are the electrons that we share. Let me back that up and do it again. We have an unshared electron here. We're going to bring in chlorine with another unshared electron, pair them up, and share them between the two atoms. We're looking for an octet of electrons, right? When you have a covalent bond, you count the shared electrons for each atom. So for this chlorine, we have 2, 4, 6, 8. For this atom, we have 2, 4, 6, 8. They both have a full octet of electrons. When we draw a covalent bond in chemistry, we typically don't use little dots. We typically use a dash. The dash looks like this. Whenever you see two atoms connected by a dash, you should know immediately that this is a covalent bond containing two electrons. Any questions? Well, let's make a molecule. How about ammonia? Ammonia has one nitrogen and three hydrogens. What we're going to do is look at the periodic table. We're going to find our atoms. We're going to bond them together such that we form 8 valence electrons around the nitrogen and 2 around the hydrogen. So, start off with our nitrogen. When you have more than 2 atoms in a molecule, the way it's written describes the central atom and then things that are attached. So the central atom always comes first. So our nitrogen is going to be in the middle. Now we're going to add our 3 hydrogens. We arrange these in our Lewis structure so that the unshared pairs line up with each other. That's because we're going to scooch these guys all together, and we're going to make 3 covalent bonds. Our nitrogen now has 2, 4, 6, 8, and every hydrogen has 2. Everybody's happy? And we show it like this using dashes. We show our unshared pair, and we show 3 covalent bonds holding 2 electrons each. Any questions? Pretty simple, isn't it? Let's do one that's a little more complicated. Molecular nitrogen, nitrogen in the air, exists as a diatomic molecule, two nitrogens stuck together. Okay? Well, nitrogen is here in group 5. That means we have 5 valence electrons on each. So let's put them in there. Oops. Let's put them in there. And let's see what we have. Clearly we can make a bond here. Okay? So for this nitrogen, that would be 2, 4, 6 electrons. Same thing for this one. 2, 4, 6. 6 is fine, but it's not 8, is it? So what we're going to do, because this is simply bookkeeping, is rearrange these electrons so that we wind up with octets. We're going to start by taking these unshared electrons, move them in. When we do that, we wind up with 2, 4, 6, 7 electrons around each nitrogen. 7 is better than 6, but it's still not 8. To get 8, we're going to take these other unpaired electrons, move them in, and this is our structure. Scooch it all together. This nitrogen has 6 electrons that are shared and 2 more. That's 8. This nitrogen, 6 electrons and 2, it has 8. Nitrogen is held together by 3 covalent bonds. That makes it a very, very stable molecule, actually. Takes lots and lots of energy to break these bonds. Ammonia, which we saw a little bit ago, is used in agriculture for fertilizer. And it was a great triumph for somebody to figure out how to take nitrogen, break these bonds, and make ammonia. They're very, very, very resistant to breakage. Any questions? Well, let's do one more example that's slightly different. Carbon monoxide. Carbon is here in group 4. Oxygen is in group 6. Total of 10 valence electrons. We're going to rearrange these so that we wind up with 8 around each. So this is what we have. 4 from carbon, 6 from oxygen. I have arranged them with the unshared pairs lining up. The way this starts out, this oxygen has 2, 4, 6, 7, and the carbon has 2, 3, 4, 5. So let's do like we did with nitrogen and start off by moving these guys in. When we do that, all of a sudden our oxygen is very happy. It has 2, 4, 6, 8, but poor carbon only has 2, 4, 6. Oxygen is very benevolent and doesn't mind at all sharing nicely, so we're going to take this pair, move it up, and we wind up with this structure. Now everybody has 8, but there's one thing that's wrong here. When you have an unshared electron like this makes the molecule very reactive. Electrons like to be paired up. So if you ever have leftover electrons like this, try your best to pair them up. So we're going to move this up here, and this is our final structure. The carbon has 8 electrons, and so does the oxygen. Another example of a triple covalent bond. Each one has 3. We have 3 covalent bonds, each one with 2 electrons. Any questions? the way I did all of this stuff, it's just kind of like freelancing, okay? I do it by inspection. There are people that like rules. And yes, there are rules for Lewis structures. In the tutorial is built using the rules. So if you like rules, if you think that that's a simpler approach, go ahead and do the tutorial and just take a look. Here we're looking for CO2, carbon dioxide. First thing, we're supposed to count the total number of electrons and the total number of hydrogens. Well, there are no hydrogens. That's obvious. Electrons. We look at our periodic table. We have carbon and oxygen. 2 oxygens. We have 4 valence electrons on the carbon, and we have 6 times 2, 12 on the oxygens, for a total of 16 valence electrons. All right, that's rule 1. Next, we're going to take the central atom. And again, we have 3 atoms here, so carbon is the central. And we're going to write the carbon, put the oxygens on both sides, and we're going to give each oxygen an octet of electrons. So, let's draw it this way. There's our carbon, we have 2 oxygens, and we have an octet around both. The next rule, place any remaining electrons around the central atom. Well, remember we had 16 electrons, didn't we? By George, we've used them all. Okay. Last rule. Make double or triple bonds if necessary to give the central atom an octet. Well, with carbon dioxide, we could do it this way. We have 8 electrons here. We only have 4 here. We could take these guys, move them in, these guys, move them in, and wind up with this as our structure. So, the tutorial has a library of structures and basically shows step by step as you go using these rules. If you like the rules, that's fine. If you just like to go freelance, that's fine too. Any questions? Now the tutorial quiz on Blackboard is totally different than this. We'll talk about that in a minute. But first, let's talk about exceptions to the octet rule. You can't have rules unless you have exceptions, can you? This is SF4. 1 sulfur, 4 fluorines. This is its geometry in real life. If you look at our central sulfur here, it has 2, 4, 6, 8, 10 electrons around it. All right. The reason it can do this, sulfur is in the 3rd period. Remember, things in the 3rd period have d orbitals available. They're not filled yet, but they have them there. We simply put this extra pair of electrons in the d orbital. This is called valence expansion. Let's take a look at it. How do we do this? We have SF4, 1 sulfur, group 6, 6 electrons. We have 4 fluorines right here. They have 7 electrons each. So, we're going to put our atoms here. Our sulfur was 6, and our 4 fluorines with 7. Right away we see, okay, we had 2 unshared electrons here. We could pair those up with fluorine, no problem, right? But between the sulfur and fluorines up here, these have 3 electrons. Covalent bonds can only hold 2. So, to do the Lewis structure, since it's just bookkeeping, what we're going to do is take this extra pair, our problematic pair, and we're going to get rid of them. Where are we going to put them? I'm going to put them in something called storage, which is the corner over here. All right, so we have 2 electrons in storage. Now it looks really simple, doesn't it? We have 1 bond, 2 bonds, 3 bonds, 4 bonds. Make our dashes, but we have to remember we still have 2 electrons sitting here in the corner. We have to put them back, and they go on the central atom. That's the sulfur. And that is SF4. Valence expansion. Anything in the 3rd period going down can do valence expansion. This is what it really looks like with its electron pair sticking out. Again, in general chemistry, you might learn that this is called a hybridized orbital, where we take 1 s, 3 p's, and a d, and calculate regions of space where the electrons will be, and it gives us this geometry. Any questions? Now, yeah.
You said 3rd period, not 3rd group, right?
I'm sorry?
For the exception, it's the 3rd period, not the 3rd group, right?
Right. 3rd period down can do it. Now, when you go to take the quiz on Lewis structure on Blackboard, you will get questions that often look like this. In the Lewis structure for ClF3, there are blank electrons around the chlorine and X number of double bonds. Okay? In order to figure this out, you need to do a Lewis structure for ClF3. So let's do it. Chlorine is here in the 7th group. It has 7 valence electrons. Each fluorine will also have 7. And we have these as our atoms. Now let's follow the rules here, okay? First rule, count the number of valence electrons. We have 7 times 4, 28. Second rule, we're going to make an octet around each of the fluorines. Okay? Third rule, we're going to put remaining electrons on the chlorine. Well, we have used 8 times 3, 24. We have 28. We have 4 electrons left over. Put them on the chlorine. Let's make our dashes. Again, this is valence expansion because chlorine, the central atom, is in the 3rd period. So, you do this, then you go back to Blackboard. In this Lewis structure, there are how many electrons around the chlorine? 2, 4, 6, 8, 10. How many double bonds do we have? 0. Any questions? Now, most of the questions on Blackboard don't involve valence expansion. but there are 2 or 3 in there in the data set that do. So just do it that way. Any question? Well, there's a very important question. I said that there were 2 types of compounds. Molecular compounds where we share electrons, and ionic compounds where we transfer electrons from one to the other. How do you know which you have? Turns out it's very, very simple. This is a molecular compound. We have covalent bonds, 2 here, 1 in each of these. And this is an ionic compound, sodium chloride. These are going to form electrostatic ionic bonds because they're simply attracted to each other. Way you tell what you've got is to think about the colored periodic table we saw in chapter 2. We said that everything in blue here was a metal. We said that everything in yellow was a nonmetal. And these little green guys at the interface were semimetals. If your compound only contains semimetals and nonmetals, it will be molecular and have covalent bonds. The easiest rule to remember, however, is for ionic. If your compound contains a metal at all, it will be ionic. So what you do is you look at your compound, decide if it's got a metal. If it does, it's ionic. If it doesn't, it will be molecular with covalent bonds. Magnesium chloride. We look at our periodic table. Magnesium is here. It's a metal. Chlorine's a nonmetal, but we have a metal in there. It's ionic. Hydrogen fluoride. Hydrogen's on this side of the periodic table, but remember, it's unique because actually it can be either a metal or a nonmetal. But typically we think of it as a nonmetal. This is a nonmetal. Fluorine's a nonmetal. We have a covalent molecular compound. Silicon tetrachloride. Silicon is here. It's a semimetal. Chlorine, of course, is a nonmetal. This is molecular with 4 covalent bonds. Sodium bromide. Well, that's simple. Sodium, we all know sodium now. It's a metal. If it's got a metal, it's ionic. And finally, I said that nitrogen exists as N2, right? Chlorine, Cl2. Oxygen is actually O2. The diatomic molecules are very important. We'll talk about those soon. But sulfur exists as S8. 8 sulfurs stuck together. My question is this ionic or is this molecular? Well, sulfur is here. It's a nonmetal. That means that all 8 of these covalent bonds are going to be in a molecular compound. That's what it looks like. It's kind of like a crown. It's kind of cute. S8. Any question on the concept here? Pretty simple. It has a metal. It's ionic. All right. Nickel chloride. We look at our periodic table. Look around trying to find nickel. Well, there it is. It's a metal. It's ionic. Dihydrogen sulfide. We find hydrogen. We find sulfur. They're both nonmetals. It's molecular. Silicon tetrahydride. Silicon. Hydrogen. Semimetal, nonmetal, molecular. Sulfur trioxide. Sulfur is here. Oxygen is right above it. Both nonmetals. And calcium hydride. Calcium is there. It's a metal. It is ionic. Very quickly look at this next list. I will hush for a second and just jot down molecular or ionic. On the exam, everyone will have a periodic table. It looks like this one, except no colors. Cesium oxide. Cesium, where is cesium? It's right there in group 1, isn't it? It's ionic. Diiodine heptaoxide. Iodine, oxygen. They're both nonmetals, molecular. Oxygen difluoride, both nonmetals. Carbon tetrahydride. This is also methane. Remember we saw the structure of methane. Carbon, hydrogen, nonmetals, molecular. And finally, sodium chloride, that's the given. Sodium is right there, it's a metal, it's ionic. So, it's pretty easy to figure out what you're dealing with, right? That's important to know because the nomenclature for ionic and molecular differ. Let's start off just talking about ionic compounds again, and then we'll move into their nomenclature. Ionic compounds, sodium chloride, sodium, chlorine paired up. They're always 1-to-1 ratio. And again, they're held together simply by electrostatic forces. If you look at a crystal of sodium chloride, it looks like this. Beautiful little crystals. These are cubic, and they're cubic because when sodium and chloride pack together, they form a cubic matrix. This matrix just continues to grow and grow and grow, and as it does, it forms a distinct cubic structure. When you're putting an ionic compound together, you need to be able to predict what the charge is going to be on each ion. The way to do that, quite simply, is to look at the group numbers again. For the first 4 groups, it is energetically more favorable for the metal to lose an electron and become a cation. So things in group 1 will be +1, +2, +3, and +4. They all form cations, the metals do. Down here, tin and lead. Okay, once we get to group 5, it becomes energetically more favorable for the atom to accept electrons. So something in group 5 will accept 3 electrons to give it noble gas, and it will become a -3, a -2, and a -1. So group 4 is where we change. These are all cations, and these are anions. When you're building a molecule, you have to remember that the thing you build, the ionic compound you build, has to be neutral. This is called the principle of charge balance. You must have the same number of cations, charges, as you do anion charges. Magnesium and sulfur. This is group 2, this is group 6. +2, -2. Put them together, we get a net charge of 0. Sodium bromide, +1, -1, again 0. If we wanted to pair sodium with sulfur, sulfur has a -2 charge, it's group 6, sodium group 1, so we need 2 sodiums for every sulfur. And finally, the opposite, magnesium, group 2, bromine, group 7, we need 2 bromines for every magnesium. Principle of charge balance, you must wind up with a neutral molecule. When you write the structure, the rule is very simple. We're going to do the simplest, the lowest whole number ratio of the atoms. So if we have magnesium and sulfur, +2, -2, we would write this simply as MgS. If we wrote it Mg2S2, that's wrong. The lowest whole number ratio. Sodium bromide, +1, -1, NaBr. Here we have 2 sodiums and we have 1 sulfur. Again, we show this using this subscript after sodium to show we have 2 sodiums for every sulfur. 1 magnesium, 2 bromines, 1 magnesium, and Br2. Going backwards, if we look at formulas, we write NaCl. That tells us we have 1 sodium, 1 chlorine, 1 hydrogen, 1 fluorine, 2 hydrogens for every oxygen. That's 1. This is 2 potassiums, 1 sulfur, and 4 oxygens. Any questions? Well, let's just write a simple compound or 2. Magnesium and chlorine. First thing we want to do is find them. Magnesium is here. Second group, it's a +2. Chlorine is here in group number 7, so it'll be a -1. We need to come up with a ratio so that we can balance the charge. We need 2 -1s to balance our magnesium. By inspection, we could simply write magnesium, Cl2. And that's magnesium chloride. Now, it's not always this easy. sometimes it's a little trickier. Here's a classic: aluminum and oxygen. Again, aluminum is here in group 3, it's a +3. Oxygen is here in group 6, it's a -2. So we have a +3 and a -2. We have to come up with a ratio that will give us a net charge of 0. Now, once again, this isn't rocket science. You could do this in your head, but there's a cute little symmetry thing you can do that's actually useful as we go on. We have aluminum and we have oxygen. +3, -2, right? Let's just write AO. Look at the charge of this is +3, right? The 3 here will represent the number of oxygens in the compound. The 2 here, ignore the fact that it's negative, the 2 here will represent the number of aluminum. And our compound is Al2O3. Crisscross. If you think about it the long way, each aluminum is +3, this is 6 positives. Each oxygen is -2, this is 6 negatives. Simple crisscross. When you do crisscross, however, you have to be careful about lowest whole number ratios. Let's say we did beryllium and selenium. That's a +2 and a -2. So if we wrote this and we did our little crisscross thing, we would get Be2Se2. That, of course, is wrong. Lowest whole number ratio is simply BeSe. This is what it looks like. And I put this in to stress that ions have different sizes. And that's why we have different crystal shapes, the way they pack. Turns out that this is cubic as well. But the beryllium is a little tiny thing. The selenium is quite large. Again, different sizes for different ions. Okay, as I've been talking about these things, I've said things like beryllium selenide. I'm sure you're all sitting back and wondering, how do I know that's its name? Right? Right. That's because the rules for nomenclature for ionic compounds are really quite simple. What you're going to do is take the cation. Whatever element it is, it will be the first word of the name. You will then take the anion. You will look at it and think for a second. If it's like chlorine, you would say, what is the root of that word? It's chlor. So you would take the root and add IDE. This compound, our first element here is magnesium. We would simply write magnesium. Because this is an ionic compound, we will not use multipliers in the name. We will simply say, this is magnesium, this is bromine, the root is brome, and we will add IDE. That's it. First element is sodium. We write sodium. The root here is chlor for chlorine. And we add IDE. K is potassium. The root for sulfur is sulf. And we add IDE. Beryllium and bromine. IDE. That's all there is to it. Don't have to worry about multipliers at all. Now we'll see that this is very useful going in one direction and a real pain in the other. But let's do the easy one first. Look at these guys and quickly jot down names. All right, our first one here. Ca is calcium. We would write calcium. Leave a space. The root is brome. We would make this bromide. Calcium, bromide. Al is aluminum. We will write the word aluminum. Leave a space. Root here is ox. We will make this oxide. Li is lithium. We will write the word lithium. This is sulfur sulfide. Calcium again. Root is ox, oxide. Nickel. First word. This is chlorine, so it's chloride. Now actually, we'll see in just a couple minutes, this is wrong. Looks right, but it's wrong. Actually, it's nickel 2 chloride. And that's because nickel is a transition metal. Transition metals can have different charges. So you have to show the charge in the name this way. But we'll talk about that in a minute. So that's the easy way. Taking the formula and getting an A. Let's go backwards. I will do the first one with you, and then I will let you complete the list. What you want to do here is look at the cation, decide what the charge is. Same thing with the anion. Calcium is group 2, it'll be a +2. Nitrogen is group 5, it will be a -3. This is where you can very easily do your crisscross in your head. 3 calciums, 2 nitrogens. Go ahead and run through the rest. Magnesium is group 2, +2. Oxygen group 6, -2. Simply want 1 to 1. Lithium is group 1, +1. Iodide group 7, -1. Once again, 1 to 1. What's the charge on barium? It's group 2, so it's +2, right? Phosphorus is here in group 5. It will be a -3. Three bariums for every 2 phosphorus. Isn't that handy? It's kind of handy. Beryllium fluoride, beryllium at group 2, +2, fluoride is group 7, -1, 2 fluorines for every beryllium. Any questions? All right. If this is all there was to naming ionic compounds, number 1, we'd be done. And number 2, it would be remarkably simple, wouldn't it? Sadly, there is another class of ions called polyatomic ions that make it somewhat more complicated. Polyatomic ions is a group of atoms that are bonded together covalently. It's a molecular ion. These combine with simple metals to form complex ionic compounds. Strontium sulfate is the example we're going to look at. Strontium is right here in group 2. It's a +2. This is sulfate. This is 1 sulfur and 4 oxygens. This entire complex has a -2 charge. If you look at the bonding here, this sulfur has 2, 4, 6, 8, 10, 12 electrons around it. It's busy. SO4, and it has 2 negative oxygens. This is a polyatomic ion. Now, when you think about a polyatomic ion, just think about it as a ball. Okay, it's a unit, it's a thing. Strontium and sulfate pair up. Strontium, sulfate, whatever. Just like sodium chloride. Except this is big and ugly and whatever. Okay? The real problem is there are lots and lots of polyatomic ions. This is something from the book, and believe it or not, you kind of need to know lots of these. Yeah, you do. Carbon-containing acetate carbonate, hydrogen carbonate, cyanide, chlorine-containing perchlorate, chlorate, chlorite, and hypochlorite, etc., etc. There is one little trick, though, that makes this a little bit simpler. If you notice, these guys all are bonded to oxygens, right? For oxygen-containing polyatomics, we can identify one particular polyatomic ion, and we'll call it the parent. So if we have chlorine with 3 oxygens, the chlorine would be the parent, that's ClO3, and we would label that as chlorate. Chlor, the prefix, 8, the suffix. That's the parent. If we now take the parent and we add 1 oxygen to it, we keep the 8, but we put a per in front. If we take the parent and take 1 oxygen away, we change 8 to ite. And if we take 2 oxygens away, well, we keep the ite and put a hypo in front. The thing that's neat is that once you remember the parent here, this is a -1. All of these will have the same charge. So it does make it simple in a way. Just remember the parent, add or subtract oxygens, all the same charge. For example, here we go. Again, for chlorine, our root here is chlor. This is the parent. We will call this chlorate. If we add one oxygen, we'll have ClO4, right? Keep the 8, call it perchlorate. Take one oxygen away, ClO2. Change the 8 to ite. Take 2 oxygens away, keep the ite, and put hypo in front. Bleach is sodium hypochlorite. All right, I know this isn't trivial. It's a lot to think about. But by the time of the exam, we will look at enough examples that the ones that are on the exam will seem simple to you. Promise. For sulfur, the parent is sulfate. Take one oxygen away, we get sulfite. This is what it looks like. We saw this earlier. We have 2 negative oxygens. When you have 2 negative oxygens, you can actually take a hydrogen and attach it to one of them. When we do that, we get this structure. We call this hydrogen sulfate. If you note, the charge has gone from 2- to -1. That's because the hydrogen comes in as a +1 ion and neutralizes it. So this is sulfate, this is hydrogen sulfate. Do the same thing with sulfite and get hydrogen sulfate. Phosphorus. Phosphate's the parent. Phosphite, 1 oxygen away. Here we have 3 oxygens. We can add a hydrogen to 2 of them. So we get hydrogen phosphate, looks like this, and dihydrogen phosphate. When you write the words, the name, hydrogen and phosphate are separate words. Carbon. The parent here is carbonate. There is no carbonite. That was Star Wars. Carbonate, again, has 2 negative oxygens. We can add a hydrogen and make hydrogen carbonate. Well, shoot. This is acetate. Acetate has a carbon with 3 hydrogens bonded to a CO2-. We're not going to do much with acetate, but in general chemistry, you would live and die by acetate, okay? So, yeah, you want to know what acetate is. It's also written in the condensed formula here, which makes no sense to me. This is what it really looks like. Cyanide, everybody's favorite poison. Triple bond between the carbon and the nitrogen, -1 charge. Nitrogen. Nitrate is the parent. Nitrite. This is the only cation that we're going to deal with. 1 nitrogen, 4 hydrogens, and a +1. When you do the tutorial, once again, this was written for general chemistry, sorry, but there are a couple that show up. Chromium-containing ions are one of them. There are 2 things here, chromate and dichromate. This is what they look like. They're both -2. This is used in cleaning solution. It's a very powerful oxidizing agent. It's used to get scum out of glassware and stuff. So you use this a lot in general chemistry also. All right, let's look at a polyatomic ion in terms of its Lewis structure and see where this charge comes from. Let's do chlorate, the parent of the chlorine group, right? -1 charge. Chlorine is here in group 6, group 7. Oxygen in group 6. We have 1 chlorine and 3 oxygens. Now, as we arrange this and look at it, that's kind of a mess, isn't it? Couple things we need to do. We have 3 electrons here. Again, it's simply bookkeeping. You just look at it and say, well, I wrote it stupid, right? Let's take one of these, move it up, and this one, and move it up. When we do that, we would have 8 electrons around each oxygen. Here we have an unpaired electron. Let's take this guy and move it down. When we do that, we wind up with this. Now, very clearly, we can do 8 electrons around the oxygens, but we have 7 around here. Now, that's not a problem, because what's the charge? It's -1. So, sodium, for example, will give up 1 electron. It will donate it to this structure, like this. And this gives us chlorate anion. We have 8 electrons around the oxygens. We have 8 electrons around the central chlorine. We would write it something like this. Again, you must show that this has a negative charge. This is a lump with a negative charge. Now, the negative charge really isn't on just the chlorine. It's somewhere here in the complex. We have an unshared pair here that's sticking up. We'll see someday that this is called tetrahedral geometry. But nonetheless, we have 1, 2, 3, 4 things bonded, makes it tetrahedral. Somewhere in here is an extra electron. Make sense? All right, when you go to name something that's polyatomic, you simply take, just like the other, the cation and then the polyatomic ion. This is carbonate, isn't it? This is calcium. We would call it calcium carbonate. This is the only cation I said we're going to deal with in H4. Ammonium. This is chlorine, so it's chloride. Ammonium chloride. This is sodium. Sulfate has a -2 charge, so we need 2 sodiums. We do sodium sulfate. If we take sulfate, take 1 oxygen off, what do we get? Sulfite. Lithium sulfite. Phosphate is PO4, isn't it? It's a -3. Here we put 1 hydrogen on, making this -2. So we need 2 potassiums. Potassium, hydrogen, phosphate. 3 words. Going backwards is also challenging sometimes, but because we don't have multipliers. But look at these. The thing that you need to know here is what sulfate is, what sulfite is, what nitrate is, blah, 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 right? So, we're going to have exam 1 pretty soon, after chapter 4. First, we have a sample exam, where we'll go over it in class. Then we'll have the real one. When you take the real exam, as a memory aid, you are allowed to bring one 3x5 card. That's 3 inches by 5 inches, not 3 feet by 5 feet. And you're allowed to bring one of them with whatever you want written on one side. So, if you have trouble remembering what sulfate is, write it down very small. Okay? So, sulfate is SO4, -2. Potassium, group 1, +1. We need 2 potassiums for every sulfate, K2SO4. See if you can run through the rest. Barium is group 2, it'll be a +2. Sulfite is sulfate -1 oxygen, but it's still -2. 1 barium, 1 sulfite. Aluminum is group 3. Chlorate is -1. So we're going to need 3 chlorates for every aluminum. Now, how do we show that? We're going to have to take the structure for chlorate, put it in parentheses, and then show we have 3 of them. It would look like this. Here's our aluminum. Each chlorate is -1, and we have 3 of them. Silver nitrate. Silver is actually a transition metal, right here. In spite of that, silver is always +1. Just remember that. Silver, +1, nitrate. The parent of nitrogen is -1. 1 silver, 1 nitrate. Finally, barium is group 2. Cyanide, we said, was -1. We're going to need 2 cyanides for every barium. Again, we show it by taking the structure of cyanide in parentheses and showing we have 2 of them. If we didn't have the parentheses, we would look at this and say CN2. Carbon with 2 nitrogens. Nope, not that, not that. Enclose the whole thing in parentheses and then say how many you have. Any questions? right, well, it does get even more complicated. I apologize, not my fault. But let's look at these. Name these compounds. Simple. Pb is lead, Fe is iron. We don't use multipliers, right? Lead oxide. The next one. Lead oxide. No multipliers. Iron oxide. Iron oxide. Iron oxide. Clearly, there's a problem here. Again, lead and iron are transition metals. They can have different charges. We'll see we just have to change our name to include the charge. Now this is called the oxidation number. That's a fancy word for the charge. When we do chapter 5, we will talk a lot about oxidation numbers. Oxidation numbers are really simple though. Take the atom as it appears in the periodic table. You're going to determine its charge. It'll either have more electrons or less. It'll be negative or positive. That's the oxidation number. So if we're dealing with something like magnesium bromide, we would say magnesium group 2 plus 2, bromine group 7 minus 1. In the terms of oxidation numbers, we would simply say the oxidation number of magnesium is plus 2, of bromine is minus 1. Same thing. Lithium plus 1, phosphorus minus 3. Oxidation numbers, the same thing. Now, in chapter 5, we will meet a set of rules that talk about how to assign oxidation numbers to everything, including nonmetals. This is what the rules look like. Oxidation number of a pure element is 0. Group 1 is plus 1, group 2 is plus 2. Hydrogen. Oxygen is always minus 2, blah, blah, blah. This is the full set. Again, we will meet this in chapter 5. What you need to know now is that oxygen is going to be minus 2. Halogens will be minus 1. Halogens, again, group 7. That's all you need to know. You can know this too. What the heck? Elements are always 0. So, here we have PbO, lead oxide. You look at this and you're trying to figure out the charge on the lead. What we just saw said that oxygen is going to be a minus 2. If this is neutral, that means the lead must be plus 2. Here we have 2 oxygens. They each want to be minus 2. So this is 4 negatives, right? To make it neutral, the lead must be plus 4. Iron sulfate. Sulfate, we remember, is minus 2. To make this neutral, the iron must be plus 2. Oxidation number is charge is plus 2. Fe2O3, you could do crisscross backwards. We have 6 negatives here. We need 6 positives. Each oxygen is going to be minus 2, that's 6 negatives. That means the ions must be plus 3. So, How do we put this into the name? It's simple, really. We're going to include the oxidation number, that's the charge, in parentheses. And we're going to use Roman numerals. This is lead oxide, right? The oxygen is -2, that lead is +4. We will write this as lead 4 oxide. There is no space between lead and the 4. 1 oxygen, this is lead 2 oxide. Carbonate, we said, was -2. That means the iron must be +2. Iron 2 carbonate. Bromine, a halogen, is going to be -1. That means the iron must be +3. Iron 3 bromide. Once you think about it, it's not that complicated. You're simply putting the charge down. You have to use Roman numerals, and remember not to put a space in. There's a tutorial here that covers nomenclature of binary ionic. First thing you have to do is look at the formula and decide if your metal here is a transition metal or not. So you look at the periodic table. Barium, right here in group 2, not a transition metal. All right, so we simply write the name as barium iodide. And it tells you, yes, you got it right. That's nice. Copper. Look at your periodic table. Copper's there. It's a transition metal. We have to show the charge. We will do this. Iodine is a halogen, it's -1. The copper must be +1. You would write this copper 1 iodide. ClO, what's that? Chlorate is the parent, ClO3. We've taken 2 oxygens away, so it's hypochlorite. Each one is -1. Iron is a transition metal. We have to show the charge. We have 3 negatives. Iron must be +3. The name, iron hypochlorite. No multipliers. Any questions? All right, well, we survived this. This is a hard one. Molecular compounds are easy because you get to use multipliers. In chemistry, when we describe things, one is mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That's up to 10. And it goes. But really the ones that you need to think about are like 1 to 8, really 1 to 7, whatever. These simply describe the number of atoms in the compound. The only rule that you need to remember is that if your first element is only one of them, you don't use mono. If there are 2, you use di, tri, whatever. If there's only 1, you don't use mono. So, show how simple this is. 1 carbon, 4 chlorines. These are both nonmetals, right? It's molecular. Our first word is simply going to be carbon, not monocarbon, carbon. We have 4 chlorines. We're going to use the multiplier tetra and chloride to describe that it's the second atom in the molecule. Carbon, tetra, chloride. 2 words. How simple can it be? 1 sulfur, 2 oxygens. First word is going to be just sulfur. 2 is a di. They're oxygen, so it's oxide. Sulfur, dioxide. N2O. Here, our first atom has 2 of them. So we have to show that using di. This will be dinitrogen. Now here we only have 1 of these guys. It's a second atom though. For that you use the mono. Dinitrogen, monoxide. You'll note that I left out 1 O. Okay? In reality, if you put the O in, I would still love you. Doesn't matter. But typically when we have 2 vowels together, we drop 1. 2 nitrogens, 5 oxygens. Once again, it's going to be dinitrogen. 5 is pent. This is oxide, isn't it? Dinitrogen, pent oxide. Now actually this is penta. So we have an AO again, we just drop the A. Once again, if you do it and you put the A in, doesn't matter. Okay? Do these. One carbon, we don't use mono. 2 oxygens is a di. Carbon dioxide. 2 hydrogens, that's going to be a dihydrogen. 1 sulfur, monosulfide. 1 silicon, 4 hydrogens. 4 is a tetra. Silicon, tetrahydride. Sulfur, 3 oxygens. 3 is a tri. Sulfur, trioxide. 1 nitrogen, no mono. Nitrogen, 3 chlorines, trichloride. Any questions on these? Then let's do another set, and I'll hush.
What was the NCl3? CL3.
6.
It's from the previous.
Yeah.
No, the previous slide. Oh, nitrogen.
nitrogen trichloride. 4 is tetra. 6 is hex, or hexa. Tetraphosphorus, hexasulfide. 2 iodines, that's a diiodine. 7 is hept. Diiodine heptaoxide. I dropped the 8. Oxygen, difluoride. Carbon, tetrahydride. Tetra, sulfur, dinitride. CH4, if you called it carbon tetrahydride, nobody would know what you were talking about. This is methane. It's an organic compound. Organic chemistry has its own set of nomenclature rules. Let's go backwards. This is so simple now because the multiplier tells you exactly what you've got. 1 nitrogen, 3 iodines. 2 phosphorus, 5 oxygens. 1 sulfur, 3 chlorines. 1 nitrogen, 1 oxygen. Just say no. 1 hydrogen, 1 chlorine. When we get to chapter 8, we will learn that this is an acid. They have a separate set of rules. This is called hydrochloric acid. Nitrogen monoxide is a really interesting compound. Oh, maybe 15 years ago, it won the distinction of Compound of the Year. Okay? What made it so interesting was it's an extremely reactive compound. It has 1 unpaired electron, and because of that, anything it bumps into, it will react with. Very reactive. It was found that living cells contain machinery to generate NO. Never suspected. The reason, let's pretend this is 1 cell wall. This is the other. Somebody bumps into this side. What happens is it sets off an enzyme that generates NO. NO floods out, hits over here, reacts with another enzyme. This side of the cell says, whoops, it just hit something over here. It's intracellular communication. Really kind of neat. Okay. There is another tutorial here. Binary molecular compounds, formula to name. Here we have N2O3. You simply enter this as 2 nitrogens, that's dinitrogen, 3 oxygens, trioxide. NS. Don't use mono for the first one. It's just going to be nitrogen, isn't it? We have 1 sulfur, so it's a monosulfide. There's also a thing called name to formula. Now this is going to be a mix of molecular and ionic, okay? Our first one here, an example, sulfur tetrabromide. Now you obviously can't use super and subs, so you just have to write it out like this. All, no super subs. So sulfur, and this is tetrabromide, so that's 4 bromines. You would write it like that. In Blackboard, it's the same way. No super subs, you would write this the same way in Blackboard. Sodium phosphate. Sodium is +1. Phosphate is -3. We need 3 sodiums for every phosphate. We would write it Na, PO4 3 times. No, I'm sorry. Here, let's do it this way. 3 sodiums for every 1 phosphate. Sometimes you stand too close to the board here, you can't read it right. All right, that winds up chapter 3. We will do lab number 3 on Wednesday. Lab number 3 is density. So you want to review density calculations, do that. We will do a remarkable thing using density calculations. We're going to take a piece of aluminum foil and we are going to calculate its thickness based on the density of aluminum foil. Kind of neat. Today, we covered Lewis structures, naming ionic, naming molecular, and naming the formula. Remember, these have to all be done before the first exam. Okay, have a good day.
Bye.
Bye-bye.